So this problem here asks you to provide a mechanism for the formation of the products that you see here, and also it wants you to describe the mechanism or draw the mechanism for this reaction based on what products you're seeing. So in both cases, as you could see, you have the same substrate, which is going to be a 1, 2, 3, 4, so 3 bromo 1 butene, 3 bromo 1 butene. But depending on whether or not you have a sodium methoxide or methanol as a nucleophile, you get only 1 or 2 products here, and we are trying to understand why that is the case, that in one case you have only 1 product and here you have 2 products, and you're also trying to explain how the both the products are formed. So in both these cases we have a secondary substrate. As you could see, this is a secondary carbon since it's attached to 2 other carbons here, but the nucleophile here is a sodium methoxide, which is a strong nucleophile. And we know this is a nucleophile because if you look at the product, we have a substitution reaction, we don't have an elimination reaction. So you're just trying to look at this through the lens of a substitution reaction. And there is substitution in only one position here, which is the same carbon that the leaving group is. And since sodium methoxide is a strong nucleophile, it is going to give you a reaction by an SN2 mechanism, because secondary can go both ways, SN1 or SN2, whereas when a nucleophile is strong, the nucleophile pushes the reaction towards an SN2 pathway. Therefore, you can explain this reaction based on simply looking at the SN2 reaction. So we have the bromine as the leaving group here, and then we have a nucleophile such as an OCH3 minus, a sodium methoxide, and the methoxide is going to donate electrons to the carbon, which is the one with the leaving group, and the leaving group is going to leave, and you get the product in a single step, which is what you are seeing here. And you are going to get sodium bromide as the byproduct. So that is for equation 1, let's say. For equation 2, you still have the same substrate, which is a secondary substrate, and the secondary can go both ways. Whereas here, the nucleophile is a poor nucleophile because it does not have a negative charge, which means it is not going to proactively make a bond with the carbon, and it is going to wait for the carbon to become desperate for electrons, and that is going to happen when the bromine leaves, making the carbon a positively charged carbocation center. So the second equation is now represent a reaction which happens by an SN1 pathway, and as I just mentioned, the nucleophile is poor, so it's not going to participate in the reaction until the carbon gets into an electronic crisis. So therefore what you would expect is the bromine to first leave like that, and then you will produce a carbocation like that, and now the methoxide is going to react, so OCH3, and if that methoxide reacts, then it is going to donate electrons to the carbon, and you will get that. And when that happens, you're going to have to lose a proton because the oxygen cannot have a positive charge. So when the oxygen takes electrons away from the hydrogen and kicks this out as H+, you get one of the products that is listed there, OCH3, and HBr is going to be the byproduct. So that is one of the products here, and that is going to be, let's say here, product A. Now product B, if you look at this structure, if you look at this 1, 2, 3, 4, the methoxy group got on the same carbon, which is in the reactant. Whereas if you look at the other product, if this is 1, 2, 3 and 4, there is a shift in the position of the double bond, and the methoxy comes to the first carbon, and that is going to be possible when you take this carbocation. So I'm just going to draw this carbocation again, so it's not a chemical change. I'm going to just draw the carbocation, and this carbocation can undergo what is called as conjugation, which is again something we have seen in aromatic chemistry. These electrons can move there, and you can get a double bond between these two carbon, and the positive charge gets on that carbon, so you get a primary carbocation. And if the methoxy group leaves and becomes a nucleophile when the positive charge is on the primary carbon, then you'll have that, and this is going to lead to that oxonium intermediate, which is going to lose a proton, minus H plus, like we saw here, where the hydrogen loses electrons to the oxygen so it can get its neutrality back. You're going to get a product which is going to be the other one that is shown in the equation. So if this is 1, 2, 3 and 4, you get a positive charge, sorry, you get a double bond between the 2 and 3 carbon, and you get the methoxy on the first carbon. So that is 1, 2, 3 and 4. And that is basically very similar to what we have seen in aromatic chemistry, when the positive charge keeps hopping on to carbon 1 to carbon 3 to carbon 5. You get the nucleophile coming to different positions. So this is how we explain the formation of two products in the second equation, whereas you get only one product in the first equation, because they operate through different mechanisms, and the mechanism is influenced by whether the nucleophile is a strong nucleophile or a poor nucleophile or a weak nucleophile. Okay.